we're talking about optimization. Let's say, for example, that we had a rectangle and we wanted to find we were told that the perimeter had to be 100, but we wanted the area to be the maximum. So you could have this rectangle, a 20 by 30, or maybe a 10 by 40, or that one or that one. The question is whether or not one of these has the maximum area or some other version of the rectangle I haven't drawn yet. I gave you this in your notes. This is called the optimization recipe. So you're going to draw a diagram if it's possible, label the diagram, then you're going to create a function. The independent variable must be whatever you've been asked to maximize. And then in step 3, you're going to probably do something, either draw a picture or write another equation to put the first equation in terms of one variable. And then you'll want to do the first derivative test. You could also do the second derivative test to find the maximum or the minimum and check that your answer makes sense. So we are going to find the rectangle that has the largest possible area with a perimeter of 100 feet. So let's draw a picture. So the perimeter is 100. How would I find the perimeter of this rectangle? 2x plus 2y is equal to 100. Okay, but we want to have the largest possible area. What would be the formula for area of this rectangle? X times y. So area equals x times y. So this is what it is that we are trying to maximize. And in order to maximize, we need to find a derivative. Well, it's not going to be any fun to find a derivative right now because I have 2 different variables. So I want to get this equation in terms of one variable, either x or y. So maybe we could go back and use the perimeter information to put this in terms of x or y. Exactly. So we're going to use substitution. So I want to solve this equation for either x or y. It doesn't matter. I like y. And now I will substitute that into the other equation. So x times 50 minus x. So this is the equation that I want to find the derivative of, but before I do the derivative, maybe I should do something else first. Yeah, distribute. And now find the derivative. Yeah, so 50 minus 2x. All right, so now we're back into when we were finding a relative extrema. We needed a critical value, so you set your derivative equal to 0. And when you solve for x, what are you going to get? 25. So when we were doing this last semester, we could do the first derivative test. I'm actually going to do the second derivative test. I can show you the first derivative test as well. But remember with the second derivative test, we need to find the second derivative. If this is my first derivative, what's my second derivative? Negative 2. Okay, so d2a over dx squared. You can, of course, call it a double prime if you want, is negative 2. If my second derivative is negative the whole time, for the whole domain, what's happening with my original function? Concave down. It's concave down the whole time. So if our function is concave down the whole time, what does that mean about the 25? That's the maximum. Okay, so that means that has to be the maximum. Or you can do the first derivative test where you would set up your number line, you would put 25 on your number line, and remember you have to test values into your first derivative, and you would find that it is positive to the left, negative to the right, which means the original function is increasing, then decreasing. So that would lead you to the fact that 25 is a maximum. All right, so let's see if we've answered the question. Find the dimensions of a rectangle. Well, we have the x is 25. We need to find the y. How am I going to find the y? Yeah, so now we can take the 25 and maybe plug it in right there to get the y. We're going to get y is also going to be 25. So it's not, yeah, you're right, it's not a rectangle, it's actually a square. So the dimensions are 25 feet by 25 feet. Let's take a look at the next one. So this time we are trying to minimize surface area. A manufacturer of food storage containers makes a cylindrical can with a volume of 500 milliliters. What are the dimensions, the height and the radius, that will minimize the material in order to produce each can, needed to produce each can? And I'm giving you the formula for volume of a cylinder and surface area of a cylinder. So let's see, let's draw a picture. So the volume is 500. So let's go ahead and replace the volume in the V in the formula for 500. So I have 500 equals pi r squared h. And again, we're trying to minimize the material. So we're trying to minimize the what? Yes, we're trying to minimize the surface area. So I'm going to write this formula down again. Similar situation. This is the formula that I want to find the derivative of, but I have an r and an h, and I want it just one variable. So we'll solve the volume equation for what? Yes, let's solve this for height. And now I'm going to substitute it into the surface area equation. And that's the equation I want to take the derivative of. But before I do that, let's clean that up a little bit. R to the negative 1, because I'm going to take a derivative in the next step. All right, so you should have gotten, I'm going to call this ds over dr 4 pi r minus 1,000 r to the negative 2. And what do we want to do with that derivative equation? Set it equal to 0. 0 equals 4 pi r. Now I'm going to put that r back in the denominator. Yeah, it's exactly what I'll do. I'm going to add the 1,000 over r squared to the other side. It's like cross multiplying, so now we have 1,000 equals 4 pi r cubed. All right, so I'm going to divide by 4 pi and then take a cube root. Hopefully everybody knows how to do that in your calculator. The answer would be under math option 4. So 4.3. So this is where we would do like the first derivative test, the second derivative test. But let me be honest with you. These problems are a bit construed. They're made to kind of work out for you. I'm not trying to trick you. It's not AP calculus. So I would say 9.9 times out of 10, if that's a thing. The answer that you get when you solve is going to be the value that's going to either minimize or maximize or whatever you have. If we ended up with 2 reasonable values for r, then yeah, you would need to figure out which one is going to minimize your material. But since we only have one value here, that one is going to be the value that gives you the minimum surface area. You could confirm it by, you could go back up here and find the second derivative and do the second derivative test. You can do the first derivative test and, do 4.3 into a number line, test values into your first derivative, and it's going to end up being negative and then positive. So it is going to be the minimum. But if you end up not writing that down, I'm not going to freak out about it. Now let's make sure we've answered the question. What are the dimensions, the height and the radius that will minimize this, the surface area or the material needed? So we have the radius. How am I going to find the height? So I'll give you a moment to do that, approximately for H. So the dimensions are the radius is 4.3 centimeters and the height is 8.6 centimeters. So this is a GeoGebra worksheet that somebody made. So what we're looking at is, this is supposed to be like a rectangular sheet of paper that's like laying and you're looking at it from an angle. And what we're going to do is we're going to take this rectangular sheet of paper and we're going to cut squares out of each corner, and the squares will be the same size. We will disregard that material and then we will fold up the sides and we're going to get a box. And the challenge is to try to figure out what size squares do you need to figure out. So what size squares do you need to cut out, like really tiny squares or really large squares, so that when you fold it up you get a box that has the maximum volume given the limitations of the sheet of paper that you started with, or the size of the paper you started with. So should you cut out really large squares and you have kind of a tall box, or cut out really small squares and have a really short, wide box, or somewhere in between? From a thin piece of cardboard, 8 inches by 8 inches, square corners are cut out so that the sides can be folded up to make a box. What dimensions will yield a box of maximum volume, and then what is the maximum volume? So we have 2 parts to our final answer. So I already gave you the diagram here. Here we have our square piece of cardboard. So from here to here is 8 inches, and from here to here is 8 inches. I want the corners that I'm going to cut out, there's going to be squares. So if I call that X, and that's also going to be X. And every single corner, we're cutting out the same size square. If these squares are each X by X, and the sheet of cardboard is 8 inches by 8 inches, what's this going to be from here to here? 8 minus 2X. And what about from here to here? Also 8 minus 2X. Imagine that we've cut out those squares in the corners, and we folded up the box, and now a box looks like this. What will be the width of the box? 8 minus 2x. What will be the length of the box? 8 minus 2x. What will be the height of the box? The height will be x. Hopefully everybody's good with that information. Now we want to maximize the volume, so I need to figure out how am I going to find the volume of this box here. Now since we're going to need to find the derivative, I suggest you expand it so you don't have to do the product rule a bunch of times. You should have gotten 64x minus 32x squared plus 4x cubed, yes? All right, what are we going to do with that volume equation? Find the derivative. Maybe you already did it. 64 minus 64x plus 12x squared. And what do we want to do with the derivative equation? Set equal to 0. I'm going to reorder it. Well, 64 is not divisible by 12, but it is divisible by 4. Yes, you can use polysmalt there. It does factor to be 3x minus 4 times x minus 4. So you're going to get 4/3, and you're going to get 4. So this seems like we really will need to do either the first derivative test or the second derivative test. However, these numbers are in the context of a situation. So let's take a look at the 4. Remember, the x represented the size of the square that we're cutting out. If this is 4, and then I cut out 4 on this side, and the whole thing is 8, yeah, I don't have a box left. So we can rule out the 4 because this makes no sense in the context. So that means that the 4/3 is going to be our one and only value that's going to maximize that volume. So now let's make sure that we are answering the question. Find the dimensions, okay? So we know that the x, or the height of the box, is going to be 4/3, and to find the width and the length of the box, I need to take the 4/3 for x and plug it in to the 8 minus 2x. So take a minute and do that. So the dimensions, and then we'll have to find the volume. So the dimensions are going to be, since each width and length is 8 1/3, or sorry, 5 1/3, so we have 5 1/3 inches by 5 1/3 inches. So how are you going to find the volume? Multiply it. Yeah, I have 37.93. And what are the units on that? Cubic inches. Yep.